before the rest, and then Silke's talk. It's kind of nice to chair this session. Like all the speakers are from Waterloo, coincidentally, so it's gonna be easier for me. So the first speaker today in this session is Agata Branczyj from Perimeter Institute. I've heard that it's a really good talk, so you should listen.
Thank you, Eduardo, and thank you, organizers, for this very nice workshop. Today I will tell you about vacuum-induced decoherence. This talk is in collaboration with Olivier Simon, who is at Stanford, Alison Sachs, who is at the University of Waterloo, and Eduardo, who is right here. And so you have to make sure to ask me some questions at the end, otherwise it will be very awkward for Eduardo to have to ask questions about his own work. Okay, so let's start by imagining that you're trying to build some type of quantum technology. At the heart of this is going to be this phenomenon of quantum superposition. But any coupling of your quantum system to the environment is going to result in a loss of coherence. And so that's going to reduce your quantum superposition to some incoherent mixture of eigenstates. And so a lot of work is being done around the world in order to reduce this coupling to the environment and then increase coherence times of these quantum states. And so let's imagine a situation that we're sometime in the future where technology has gotten so advanced that we've been able to completely eliminate all possible coupling to the environment. At that point, are we safe from decoherence? Or are there some other fundamentally unavoidable sources of decoherence that are going to ruin the day? So that's the question I want to address in this talk. And I'm going to do it for a particular system, specifically an optical cavity with a quantum optical state inside. And so before we actually move on to looking at this question here, I want to just show you a little bit of what happens when we have environmental decoherence so that we can just get our bearings. So here I have a schematic of my optical cavity, and you can see that it's leaking out to the outside. So that's denoting that it's coupled to the environment. And if I were to prepare a coherent state in this cavity and evolve it for some time, what I would find, at least if I use some simple beam splitter model of loss, I would find that the coherent state doesn't decohere, but it decays, so the amplitude goes down. And so if you're familiar with Wigner functions, that just means that this Gaussian is going to go closer to the origin. Now, if I prepare a coherent superposition of coherent states, so this Schrödinger cat state, and I evolve it for some time, I find that it goes to a state that is an incoherent mixture of a cat state and this other cat state with opposite phase, which I'm calling TAC. And these little primes just denote that there is a slight reduction in amplitude. And so the Wigner function for the cat state has two blobs corresponding to the plus alpha state and the minus alpha state. And it also has some interference fringes in the middle, which tell you that you have a coherent superposition. You can kind of think about these as being analogous to the off-diagonal elements in the density matrix. And the Wigner function for the TAC state is going to look almost the same, except these interference fringes will be pi out of phase. And so when I add them together, they cancel, and what I'm left with is just an incoherent mixture of the coherent states. And you can see that they've reduced in amplitude. And one thing that's interesting is that this decoherence is much faster than the reduction in amplitude. Okay, so that's what happens in the case of environmentally induced decoherence. But what about this situation now where we have a perfect cavity? So it's ideal. By definition, it's not coupling to anything else. So quantum optics tells us that we're just going to have unitary evolution, which means that we're not going to result in any decoherence. But quantum optics fails to account for the fact that this cavity always sits in some type of vacuum state of the Dirac field. And so the thing that we want to look at today is what happens if we take into account this coupling to the Dirac field. Are we going to get some type of decoherence? Okay, so the Hamiltonian that's going to describe this interaction is the QED interaction Hamiltonian, where we have the electric charge, which is the coupling constant. We have a Dirac field, just decomposed in the standard way. It has a mass. And this couples to the electromagnetic field, also decomposed in the standard way. So this is the problem that we eventually want to build up to, but to begin with, we're going to look at just a simplified version of this problem. So in the simplified model, we want to replace the Dirac field with a charged scalar field that also has a mass m. And we're going to replace the full electromagnetic field with just a single mode of the cavity with frequency big omega. Okay, so the simplified Hamiltonian then is going to look like this, where I've now also introduced a switching function which is going to modulate the interaction, and I've also introduced a smearing function which is going to take into account the spatial extent of the cavity. Okay, so, and because we want to do evolution, we're going to do everything in the interaction picture, so I just do the standard transformation to the interaction picture and put time dependence on everything. So now if we want to model the interaction, we do it using the evolution operator, which depends on the interaction Hamiltonian. I prepare an initial state, which is the combined state of the cavity as well as the vacuum field. And then I just evolve things according to this operator. So I will do this perturbatively. So to first order, I get something that just depends on this U1 term, which is the first order term of the Dyson series expansion of the evolution operator. And it turns out that this term actually doesn't contribute, so we take things to second order and get expansion, get some terms that depend on U1 and also some terms that depend on the second order term of the Dyson series expansion. So it kind of looks messy, but everything is pretty standard. We have the smearing functions, the switching functions, the cavity fields, as well as the field operators for the scalar field. So at this point, I think it's useful to take a look at what the Feynman diagrams will look like for this interaction. So we'll do it just for the second order term. The diagrams for the term that depend on U1 look like this. So the top ones are just real pair creation, which you would expect from a standard scattering theory calculation. And then these bottom ones are the ones that we get at small times. And so we expect these to only happen at high energies, but these ones can also happen at low energies. And then the corresponding diagrams for the U2 terms look like this. They're vacuum bubbles. And I'd just like to point out that these bubbles here are not just the ones that typically get absorbed into the new definition of the vacuum state. They actually represent dynamics in our system. And so it's these bottom ones that are going to lead to some really interesting, possibly new physics, as we'll see later. Okay, so this is the slide from before. It has our state, the full state of the cavity as well as the Dirac field. But we're actually interested in the density operator just for the cavity field. So what we'd like to do is trace out the scalar field. And fortunately, the trace is linear, so that just corresponds to tracing everything out term by term. And it's at this point that we find actually this term goes to 0. Okay, so now I'm going to spare you the gory details, but essentially what we do is crank the handle for quite some time and arrive at an expression that looks like this. So you can see the first order term has disappeared, and we have just a correction that depends on E squared. We have the operators for the fields, the initial state of the cavity, the switching function, and this function little w, which we call the smeared Whiteman function, which itself depends on the smearing functions for the cavity, and then we have the Whiteman function, which we can calculate to take this form. So here K1 is a Bessel function of the second kind, and we also have an epsilon, which is a soft UV cutoff. Okay, so this is pretty much as far as we can get without assuming a particular state of the cavity. So in the next part of the talk, I'm just going to consider 4 examples of typical states that we see in quantum optics. So in the first example, we'll look at the CAT state, coherent state that we saw at the beginning of the talk. if I prepare that in an ideal cavity and then evolve for some time, I find, drumroll, a coherent state that hasn't changed at all. So we can conclude that the coherent state is robust to interaction with a charged field in the absence of charged particles. So what happens if we look at a more interesting state, let's say the squeezed vacuum state? So we can prepare that state by applying the squeezing operator on the vacuum. If we now evolve that for some time, we find it looks a little bit different. So the state evolves to an incoherent mixture of a squeezed vacuum state and a squeezed single photon state. And then we also have some coherence terms between the squeezed vacuum terms and the squeezed two photon terms. So it looks like something's happening, but if we want to actually characterize whether there's decoherence, we can do that by computing the purity of the state. So in these systems, the purity is going to range from 0 to 1, and 1 is the maximum, which tells you that there's no decoherence. And if we look at the purity to leading order in the calculations that we're doing, it actually just stays as 1. So we can conclude here that to leading order in E, this squeeze state is also robust to interaction with a charged field in the absence of charged particles. Okay, so let's look at another example, the Fock state. So now if we evolve the Fock state under the interaction, we get something a little bit messier, but essentially it's an incoherent mixture of the original Fock state, a Fock state with one fewer photon, and another Fock state with an additional photon, and then we have some coherence terms. And all of these coefficients are of order E squared. Now if we compute the purity for this state, we find that actually at leading order it does decohere. We can see the purity drops. So interaction with the charged field in the absence of charged particles does decohere Fock states at order E squared. And finally, we can look at cat states, these coherent superpositions of coherent states. So here, after evolution, under the interaction Hamiltonian, we find that the state evolves to a mixture of a cat state and this tack state, the cat state of opposite phase. So recall from before that that meant it had interference fringes that were pi out of phase, and then they resulted in a loss of coherence. So here, if we compute the purity, we find that again, at leading order, it does go below 1. So the nice thing about this expression, though, compared to the one for the Fock state, is that it only depends on one of these coefficients. So it means we have a good shot at exploring this a little bit further to see how it depends on all of the parameters in our system. So let's take a look at what G looks like. It depends, it's got these time integrals that depend on the switching functions. This function Q, which has the frequency of the cavity as well as the amplitude of the cat state. We have the smeared Whiteman function, which again depends on the Whiteman function, where this is this Bessel function of the second kind. So this needs to be done numerically, and doing 4 numerical integrals, which are highly oscillating, is pretty difficult. So in order to make progress, we want to pick some cleverly chosen switching and smearing functions to let us do some of these integrals analytically. So if we pick these ones, where we have a Gaussian smearing function and a rectangular switching function, and again, crank the handle, we can reduce this to an expression just over two integration variables, which we can perform numerically. Okay, so now let's see some numerical results. How does the purity depend as a function of the cat state size alpha? Well, we should be able to kind of see here, it's got this 1 minus alpha squared dependence, and in fact that's confirmed numerically. It decays like this as alpha grows. We can also see how the purity changes as a function of the cavity size. So we see that for small cavities there's a strong dependence on the cavity size, but then it levels off. Might also be interested, how much time do I have? Okay, great. Yeah, might also be interested to see the dependence on the frequency of the cavity. So I'm only showing you a part of the diagram to begin with, but you can see that for low energies, we have essentially it's oscillating just below 1. I think these oscillations are real, and I'll mention them on the next slide. I think this is kind of numerical noise. So it seems like it's doing nothing, But then once we get to omega equals 2, we find that there's a huge drop in the purity. And so it turns out that this omega equals 2 corresponds to the energy of the cavity being equal to the mass of the electron-positron pair. So we can interpret this huge dip as being decoherence due to pair creation, real pair creation. So now what I can do is reduce the interaction time, and we see that this dip becomes less pronounced, so the decoherence is less. But you might see that it's starting to bend down here at really low energies or frequencies. And now if I take a really, really short interaction time, we find that there's pretty much nothing here from the real pair creation, but there's now this big bend where it seems like we're getting decoherence at really, really low frequencies. And so the units that we're working in here would pretty much make one around gamma ray frequencies, but this decoherence is more pronounced at really, really low frequencies, so it might actually become relevant at optical frequencies where we expect people to be doing these experiments. Okay, and we can also look at this as a function of the interaction time. If I pick an omega that's much bigger than this energy of the positron-electron pair, then we can see that there's just this essentially linear drop in purity. As I decrease the energy of the cavity, this gradient becomes less and less. And then if I decrease it even further, we see that now there is this increasing dip. So the decoherence we can see is happening here at very short interaction times. And so we think that these oscillations are actually due to the fact that we're modeling only a single cavity mode, so there's kind of this Rabi flopping effect happening. We think if we consider more cavity modes, these oscillations will wash out, but we expect this dip here to remain. Okay, so at this point you might be wondering a couple of things. Is this the Schwinger effect that we're seeing? So we wondered about this. Oh, does anyone have any opinion? You think it's the Schwinger effect?
No, I think it's not.
You think it's not? Okay. Yeah, so we thought about this for some time. To remind you, the Schwinger effect is a process in which electron-positron pairs are spontaneously created in the presence of an electric field, causing the decay of the field. So we thought about this, and we concluded that, strictly speaking, it's not the Schwinger effect, because the original calculation was done for a static electric field, while here we have an oscillating electric field. And also the original, the effect is non-perturbative, which means that if you try to show it using perturbation theory, you would see that there's no effect. Albert is nodding. Yeah, but there were actually the subsequent work where they did show what other people have shown, that there is pair creation happening in variable electric fields. I haven't had a chance to look at them more carefully, so I don't know if they're perturbative or not. But if anyone knows, I would very much like to hear from you. Another question you might ask is this vacuum polarization? Well, we have these diagrams that are the same as the diagrams for vacuum polarization. And my level of expertise in this field extends to me reading the Wikipedia page, so I can't really comment. But the Wikipedia page says that these diagrams at the top are routinely observed experimentally, while these diagrams on the bottom have no measurable impact on any process. But we think it's these diagrams that are actually causing this bend at low frequencies. So it seems like maybe we've identified some new mechanism for actually seeing these diagrams, which you're not supposed to be able to see. 2 minutes. Okay, yeah, so that's pretty much it. I'll just summarize the results. So we've shown that some quantum optic states will decohere due to interaction with the charged field, even in the absence of charged particles. And the coherent states and squeeze states are robust to this effect, while Fock states and cat states are not. And maybe it's relevant that the first two are Gaussian states, while the second two are not. We've identified 2 different decoherence mechanisms. One of them is this standard scattering one that you might expect, this real pair creation. But also we have this finite time effect, which seems unusual. And so this one is the one that we would see at low energies, which might be actually relevant for quantum optics experiments. And so you might wonder, does this place a fundamental limit on quantum technologies? Are we going to be able to make some sort of statement, like if you're building a quantum computer and you have gates, then you can't, there's an upper limit on how quickly you can implement these gates before you start being sensitive to decoherence due to vacuum interactions. So that's something we would like to explore. Thank you very much.
Thank you, Aggie. We have questions now. Miles first, then Ralph, then Rob. And then Alex.
First?
Oh, I have two questions, but
Okay.
I'll save one till later. So,
Okay.
so you're using QED?
Sorry?
You're using scalar field QED. Or,
Yeah, there's a scalar field.
but
Yeah.
but there's also another interaction process where you have a squared phi squared, and you're just using a phi squared. And I thought you need both for gauge invariance.
Yeah, I don't know how to answer that. Do you want to answer that, Eduardo?
This is just to show how this interaction turns with the coherer. You would have, of course, if you do full QED, you need electromagnetic.
Full scalar field QED.
For scalar field. No, this is basically, what we're doing here is neglecting polarization effects. So we're treating the electromagnetic field as a scalar field. And the gauge freedom there is U1 as well, and it's fixed. It's gauge invariant.
Thanks.
Thank you for letting me say.
Anyone else?
Ralph.
Did you check out how much of this is an artifact of the suddenly switching on and off? Since I think most of the, or I could imagine a lot of this is just since you suddenly switch on and off, and if you don't have that, then I could imagine a lot of these effects go away.
Yeah,
Did you check that?
Absolutely. No, that's exactly the effect. Like, that's the point. That it's so the point is that if you start now doing gates quickly, turning them on and off quickly.
No, I mean you switch the interaction between your field and the Dirac field on and off.
Yeah.
And that's sort of the problem. Maybe not with the pair creation, but in other cases I would say it's the switching. But maybe you can.
Okay, Eduardo's dying to answer. Yeah.
The effects are scale effects. So keep in mind that we have a Gaussian mirroring. So the violence of the switching is totally smeared out in frequencies by the Gaussian mirroring. What is important is the scale, the duration of the interaction, not the discontinuity. You can repeat this with a Gaussian one, you would get the same result, similar. Shape will change a bit. And we can discuss much later if you want. Yeah. Sorry.
Yeah, sorry, I didn't quite understand the question.
Alex now?
Albert.
Rob. No. Rob was first.
Well, I'm sorry. And I just wondered, in those graphs you had where you changed the time, what units is the time in?
So it's all in units of the mass. So these times, t equals 1 will be t equals 10 to the minus 21 seconds. So it's very, very short. Yeah.
Alex?
Albert.
Sorry, what am I calling you? Sorry, Albert Roberts. I know you. Sorry about that.
So I have two questions. One of them is actually related to Ralph's remark. But so if we can look at the diagrams that you have in yours.
Oh.
I mean,
Which, yeah,
the Feynman diagrams. Yeah, whichever side. Yeah, here for example. I mean, I think that on the one hand. The question of whether this is relevant for optical frequencies, for example, the contribution from, that's probably what you find, the contribution from the first diagram, what would expect is that for any frequencies which are below the Compton frequency corresponding to the mass, this diagram is not contributing.
Yeah, the top
right,
ones,
exactly.
Yeah.
And then the bottom one, at the beginning I was wondering, how do you get that bottom diagram to contribute at all? And I think it is because it's entering through the connection with the initial state. It's related to that. Somehow, this is always a tricky thing when you do these kind of calculations, because strictly speaking, what you would need to typically do is that you started with the ground state of the free theory, and then you switch on the interaction. And these things always lead to subtleties, because in some sense, what you would need to consider is that you start with the ground state, the dress state, the ground state of the interacting theory. And then in a smooth way, in a finite way, you generate then your non-trivial coherent state or superposition and so on. But there are many subtle effects that come from precisely this point, that you start with a rather sort of singular initial state, because you take the ground state of the free theory, but then because you have the interaction, it quickly sorts of dress up with all the high frequency modes of your field. So what one really needs to do, which is sometimes not easy from a calculational point of view, is that you should start with the dress state already, that takes into account the interaction with all the high frequency modes. And then many of these transient effects go away. But it's a tricky thing. However, it's something subtle that typically can be important in this.
We've definitely been thinking about this and discussing it, and I'm not sure if we've come to a conclusion as to how we want to address this, but But anyway, yeah, but
We
yeah,
could
that's
discuss
a
that
valid
later.
point,
We could
absolutely.
discuss
Yeah,
that
yeah, yeah,
later.
yeah. We can talk about it later too. Yeah.
There's one more question, Achim.
Thanks. Yes, in one of your previous slides, you said that there are two effects. One is from the suddenness of the switching, and the other is independent of that. And I think I agree with Ralph that the first one is of that kind. So you switch quickly, and you might actually pair create, and you might have that real particles will emanate. As a consequence, carry away information which leads to decoherence. And the other effect seems to be what we just heard, which is that because you're starting with a photon that is an excitation of the free theory, as time evolves, it becomes stressed. Basically, renormalization happens in real time. And so you're changing the vacuum from what it was previously, and that change in the vacuum is then carrying away information which decoheres your system.
Yeah. Is that just a comment or is there a question? Okay, great. Thanks.
Okay, very quick. We have two very quick then, because someone was before you and I was about to shut down. Oh no, Marcus, quick. And then Charis, and then that's the last.
Okay, quick and loud. Good. So, do you see any asymptotic behavior in time of if you plot the purity versus time?
You mean does it tend to some particular
Yes.
value? So we haven't taken it far enough out. Well, I mean, I only just got these plots recently, so we haven't explored what happens for long times, and I'm not sure. Yeah, I'm not exactly sure how far we can take it since this is just second order perturbation theory, but I don't see it converging to anything. If that's the question.
Yeah. My question would be looking at your low energy plots,
Yeah,
whether you will actually recover purity of 1
Yeah, yeah.
again. This is just a transient effect for low times, or whether you will
Yeah.
end up decay to some final purity.
Yeah, that's a good question, but we haven't checked it yet. Yeah.
And Gary is the last question.
This is a model that we have essentially a harmonic oscillator in a path of harmonic oscillators. Oh, thank you. Essentially a harmonic oscillator of the field in a path of harmonic oscillator.
Turn it up.
Turn it up.
In the path of harmonic oscillator with a nonlinear coupling. So there is, you can find the solution in terms, the so-called perturbative master equation, which you can straightforwardly find out the long time behavior without checking, without needing to use switch on and switch off.
Yeah, I think that's a good point, and yeah, we should look into that. Yeah.
But I also think the switch on and off is kind of important, because you were saying that's something we will talk later about.
Yeah, thanks, Eduardo.
Sorry. Okay, thank you, Aggie, again. So the next speaker.